So intuitively, we know that the rate of a reaction has something to do with the concentration of the reactants in it. All right. If you have a very high concentration of reactant, there's going to be a lot of those around, and they're going to have a better chance of colliding with other chemicals so that a reaction could occur. All right. So intuitively, we know that the rate of a reaction has something to do with with those concentrations. All right. So as we showed before, you can have the rate of a reaction at just about any given point in time. But when studying kinetics, we often focus our attention on just what the initial reaction rate is. All right. So what the initial reaction rate is, like, let's say that we have this graph here, and like we start the time right when you add your reactants. We'll call that time 0. All right. So the rate right after things are first allowed to react, that rate is going to be the initial reaction rate. All right. And we make use of that in studying kinetics. And what we're going to do is we're going to make note of what the initial concentrations of your reactants were and measure that rate. All right. And what we're going to use that for is to derive what's called a rate law. And what a rate law is it's an expression that relates the rate of a reaction, specifically this would be the initial rate of the reaction, and it relates them to the concentrations of the reactants that are in there. So for a generic reaction like this, where the lowercase letters are the coefficients in the reaction and the uppercase are the chemicals themselves, the rate, or the initial rate, would equal K, and K is going to be what's called a rate constant, times the concentration of A raised to exponent X times the concentration of B raised to an exponent Y. All right, and X and Y are generally going to be whole numbers. One thing that you might think is that these X and Y's might correspond to the coefficients in the reaction. And what I'm going to say for now is sometimes they can be the same. In fact, there's a way that would make sense for them to be the same thing, but they're not necessarily going to be the same. These X and Y coefficients are actually determined experimentally by changing the initial concentrations of your reactants and then finding out how that affects the rate. And we'll go over that in just a few minutes. So note that these are typically small whole numbers, either 0, 1, or 2. There are examples where it can be something other than a whole number. And once we know what the rates are and the initial concentrations, we can go ahead and calculate K. All right, so I'm just going to go and skip ahead a little bit and show an example of how that would work. All right, so in order to do these types of experiments, we need to have some data. All right, so here's a reaction. We're just going to say A is mixed with B. That's going to yield C and D. So what we have here, so we're actually going to run this reaction 4 different times. All right, and in each time we're going to run it, there's slightly different conditions. All right, so for example, the first time we run it, we're going to run it with a molarity. This should be, so the initial concentration, this should have a capital M after it. These are all going to be molar values. You're going to have 0.2 molar of A and 0.1 molar of B. All right, and this is what that initial rate is going to be if you have these starting amounts. So again, what that initial rate would be is what would if you could draw a tangent line at the very beginning of this reaction, right after the moment after it starts, the rate right then is going to be what that initial rate is. All right, so we measure that and then we do the experiment again. And in the second experiment, we're going to have the concentration of the products is going to be 0.2, and then we're going to slightly vary the concentration of the other reactant, and this is what the initial rate is going to be for those conditions. All right, and so we're running the exact same reaction over. We're just varying the starting amounts of the different chemicals that you have in the reaction. All right, and then we're measuring whatever initial rate that you have. So in the next video, we'll talk about exactly how you go about figuring out what the rate law is. But for this particular example right here, I'm going to go ahead and let you know that the rate law was determined to be K equals concentration of A squared, or raised to the 2, concentration of B raised to the 1. All right. So notice that I've got 4 different entries right here. And so once I know what this rate law is, all I have to do is pick one of these entries. All right. Let's say that I pick the first entry right here. All right. Well, if I rearrange this equation right here and I plug in that rate and I plug in these initial concentrations, which you can get straight from the data table right there. All right. Well, if I did that using line 1, but then I did the exact same thing using line 3 right here, all right, you would notice that you would get the exact same numbers. All right, so for a given reaction, once you know the rate law, for a given set of experiment conditions, you should always get the same rate constant. All right, and so a rate constant is going to be something that is by definition constant for that reaction. All right, you can change the amounts of the starting reagents, and that's going to have an effect on a rate, but there's going to be a constant relationship between the ratio between that rate and the amounts of those reactants. All right, so we mentioned that there are, in the rate law, there are exponents x and y. All right, and what those exponents are called is orders. All right, and the way that you say it is that a reactant is either first order or second order or 0 order with respect to that particular reagent. All right, so let's say that we had this reaction and we determined the rate law to be rate equals K A B squared. All right, well, for this particular rate law, we would say that it's first order with respect to A, and that's because the exponent after the A is a 1. It would be second order with respect to B, and it would be third order overall. All right, and so the overall order of the reaction is just going to be the sum of the exponents in the equation. All right, so 1 plus 2 gives 3, so that makes that a third order reaction. All right, so as we said before, it's important to note that the rate law can't be determined by looking at the balanced equation. All right, so if I were to show you a particular reaction right here, all right, 2A plus B, you'll see plus 2D. You can't just look at this balanced reaction and figure out what the rate law is. You have to run a series of experiments to figure out what that rate law is. And that experiment is the type that you see down here, where you just set up a bunch of different trials where you're changing the initial concentration of the starting materials and measuring that initial rate. All right, and that's based on the results of this experiment. We can use that to figure out what those exponents are. So what are those exponents? They're essentially just a mathematical description of how changing the initial concentration changes the initial rate. All right, so quite simply, the exponent of a reactant is going to tell us what effect doubling the concentration of that reaction would have on the reaction rate. All right, so if doubling the concentration of a reactant has no change on the effect of the rate, we would say that the exponent is 0. All right, or you'd say it's 0 order with respect to that reagent. If doubling the reactant doubles the reaction rate, its exponent would be 1. And if doubling a reactant quadruples the reaction rate, its exponent would be 2. So while this is the most simple way of explaining what these exponents mean, technically this is where these numbers come from. If x times a reactant were to yield x raised to the 0 increase in the rate, it's 0 order. So for example, if something, so remember, anything to the 0 is 1. All right, so for example, doubling. So for example, if we doubled the amount of a reactant, well, if we double it, x is going to be 2. So what is 2 raised to the 0? That's anything raised to the 0 is 1. That would mean it would have no effect on the rate, all right? Because the initial rate times 1 is still itself, all right? So, but keep in mind, we could still figure out the order if instead of doubling, we tripled it, all right? Because if we tripled the concentration, say we went from 0.2 to 0.6 in another trial, well, if we tripled it, x would be 3, and 3 raised to the 0 is still 1. So if doubling it didn't have an effect, tripling wouldn't have an effect on the rate. All right. For first order, it would go like this. Again, it's just going to change in that exponent there. So it's consistent with if you double a reaction. Well, what is if doubling it, x is 2. 2 raised to the 1 is 2. That would double the rate. All right. But you could also do it if you tripled. All right. If we triple the reactant, that would end up being 3 to the 1 is 3. That would triple the rate. So you could still say that it's first order. All right. We said that doubling the reaction, if it's second order, doubling the reaction quadruples. So if we double the reaction, x is 2. But if we take 2 and we square it, that's going to be 4. That's the same as quadrupling. So there can be examples where you're given only examples where they might, for example, triple a concentration. So if you saw a tripling of a reactant concentration led to a 9-fold increase in the rate, that would be second order, because tripling is a 3, all right? So if we take 3 and we square that, that would mean that the rate at the new concentration is 9 times higher than at the original concentration. So I showed earlier in the video that this is the rate law that was determined for this particular set of data right here. So let's see if we can figure out why that is. All right. So let's take a look here. Okay, in the first 2 entries here, generally you want to find a situation where one of things stays the same and one of them doubles, or one of them triples. So in this case, this is between the first and the second one, this is really useful because A stays the same, but we can see that B doubles. All right. And so let's see what happened here. Well, that caused the rate to double because this is twice as much as this. So what that tells us is that this reaction is going to be first order with respect to B. All right. Doubling the concentration of B doubled the rate. All right. So if you look at this right here, you can see that B ends up having a 1 exponent there. All right. So let's see what we can figure out about A. So we want to find a situation where the other thing stays the same. So there's actually 2 places we could do it. We can see going from here to here, that B stays the same, but in that same course, A is going to double. All right. So what happens? Well, in going from this to this, that's a quadrupling. All right. So doubling A at constant B causes a quadrupling. That means it's going to be second order with respect to A. So that's why we have that that exponent right there. Again, if once we have that, if we need to figure out what K is, we just pick any of these and plug the numbers in, and we can figure out K. You might notice, hey, there was 2 places where we could have figured this out. There was also this place here. B is staying the same here, and A is doubling there. All right, so it shouldn't matter. All right, notice that at constant B, if you double A, look at what happens to the rate. All right, so it might look a little odd because this number right here is still 4 times greater than this number right here. You have to pay attention to the exponent right there. So in the next video, we'll talk a little bit more about the units, and hopefully that makes sense.